Hello, I'm Ted Grossart. This is a series of lectures for the course Public Participation in Public Goods offered here at UK. This particular lecture is taking us deeper into some of the more detailed work that we've previewed in earlier lectures. So this particular lecture is going to talk about the use of fuzzy set analysis for complex and nonlinear scenarios. So just to orient you, in the course, we've had a theory section, we've had an analysis section, and we're now into the process section. And we're sort of toward the end of the process section. Today I'm going to talk more about the fuzzy set analysis and give you some mini case studies to give you a feel for how you can use this to solve different types, different content type problems. It's a very versatile tool, and so I want to help you understand it a little better. I think you would find it very useful when you're in particularly complex, or as they call, wicked problems. So it's a little bit of review. As we said in the last lecture, that fuzzy set analysis is the kind of approach, the math of it allows us to measure data from about a 10% sample of all possible outcomes and then model the results. And it relies on the fact that each variable or each factor that composes the solutions has a linear or logical continuity to it. And so it can model the space in between two points on that continuum that you might not have directly sampled. So it relies on that as an assumption that helps it to work. But it is very useful when you're trying to solve problems of high complexity and you have large groups of people. So you can't sample many dozens of outcomes with them, or in some cases hundreds of outcomes. It's simply not, it's beyond the capacity of people to do that unless you bring them in for multiple sittings, at which point you have created other problems. If you remember the QICE analysis, not everybody can come to a whole bunch of meetings, and so now you will induce a problem with inclusion, you reduce your sample size, and the data that you do gather will be suspect because you can't be sure that you've sampled enough people to know what's going on. So it's a kind of Occam's razor kind of problem that we are attempting to solve. This is one of the methods for attempting to solve that. So these samples, as we mentioned before, need to be carefully chosen. It can't just be random throwing darts at the board in terms of the dispersal. They have to be chosen so that they purposefully catch as many of the different factors and their values at least once as possible, so they're evenly distributed, and we'll talk about that a little bit. But it does mean that if you have an outcome where there are 150 possible scenarios, you can do a decent job of modeling preferences by only showing them perhaps a dozen or 15, something between 5 and 10% of them. This would be the kind of situation I'm talking about here would be, for example, land use patterns for rewriting a comprehensive land use plan. There are many combinations, and we'll look at some of these. But this would be a typical problem that you would run into, is that the outcomes are multiple, complex, they're not linearly related, and you can't possibly show them all to everyone. So, and also many of the kinds of variables or factors that we are talking about, they're not high precision types of variables. They tend to be more sort of categorical, so they'll go from low to high, or low to medium low, to medium high to high, those sorts of things, which will have numerical values attached to them. But in terms of in terms of distinguishing the different values for a particular variable, probably a categorical categorization of them is basically all people can discern anyway. So it helps that many of these problems are like that. They're not high precision. They're just very complex with a range of variables that range from, say, low to high, maybe 3 to 4 to 5 categories for them. So there are some boundary conditions for how you use this, and you'll see this as we go through the examples. So again, a review, we talked about how you could use these design codes for bridge architecture, and we talked about how with the bridge architects we designed one factor was just the shape of the superstructure, and so we just named it. We said it goes everywhere from A, where the tops touch, to H where they're vertical, and then you can imagine the continuum in between where they're slightly slanted in and everything in between. So there is a logical continuum to that. It doesn't really have a numeric value per se, but it has a logical continuum that you can make sense of, and everyone, all the architects can agree on what it means to say you have a vertical ribs or you have ribs that touch or something in between. Similarly, with visual complexity, it's not difficult to define the two ends of complexity, and these are the visual examples we used for that. Again, the architects and the engineers defined for themselves in cooperation with us what the different kinds of designs meant visually, so that the results meant the same thing to everyone. So again, we defined the language and what it meant so that we could have a logical continuity to the factor of bridge complexity, basically visual complexity. And again, so you now can kind of see how this goes. So also this particular bridge design could have been asymmetric across the river, or partially symmetric, or completely symmetric. And again, this is a visual sampling language that we developed with the architects so that we could characterize and typify each of the bridge designs and how they were distinguished along this factor too. And so you can see here, if each of these only had 3 properties, and you put all those properties together, you've got 3 shapes times 3 kinds of complexity is 9 designs times 3 flavors of symmetric, and there's already 27 possible designs. And there were more factors that were used in the bridge design thing. So you can see quickly that characterizing even bridge designs can turn into many hundreds of possible designs. And here's the design language that we developed for the bridges. So as we talked about, the superstructure shape goes from H to A. So you see we gave it 3 values, from vertical to partly inclined to touching. The height, which is literally the height of the bridge relative to its length. And this height has a number attached to it that is assigned based on how long the bridge is. So it's a sort of ratio. But again, there was an agreement about what these values meant so that we could assign every bridge with a different height score. Visual density we just talked about, and you see that we chose to have 3 values for visual density. Within the design industry, there are some distinct structural types that they use, and they defined a continuity from truss to arch to cable stay as the continuity that they wanted to use. And then we talked about symmetrical. So now we have 5 variables, each of them with 3 values. So now we've gone from 27 times 3 is what's my math? 81 times 3 is 240 possible designs. Just from what seems like a relatively elementary coding scheme. And a moment's reflection on this will reveal that this does not completely define a design. It provides some design guidelines for a bridge designer or an architect to further refine. It characterizes the main properties of this design without specifying what the design is. There are many different kinds of, for example, vertical superstructure with low height and low visual density that are a truss type, that are symmetrical, that are completely different from each other. So to say that we have completely defined this and we've put this all in the hands of the people's preference is not accurate. We are attempting to provide decision support, just as we do with every other project, and give what's meaningful and provides clarity without dictating the designs. And so this is a conversation we typically have with the designers, the planners. We try to make clear the distinction between the information that we're gathering, which is fairly detailed and fairly clear, and the amount of running room they still have to do their jobs. So we're still shooting for that partnership on the Arnstein scale, if you remember lecture 2 about the Arnstein scale. So if you think about that for a moment, now you can start to think about other kinds of problems. So another design problem that we took on was the design of sound barriers, otherwise people call them sound walls. And you see them every day, especially as you go through urban areas. And typically there's not a lot of variation in them. They might be made of metal, they might be made of some kind of poured concrete, they might have some little design on them, they might have some elaborate design on them, but there's not been much work done on public's preference for that sort of thing. And it is an aesthetic kind of choice. So we can take this on as a design problem for state DOT, or maybe a city wants to brand their particular sound barriers in their town. And this is not unusual to see in particular towns that work on their identity in terms of sort of branding along in their public facilities, and also the sound barriers that they're building and the other kind of retaining structures they build. So measuring that in a coherent way can be worthwhile. Now, you're looking at this picture and you're thinking, this doesn't look like a sound barrier. It is, in fact, a sound barrier. And it gives you an idea of the range of considerations that can go into the design of a sound barrier from an aesthetic point of view. So we worked on this instead of with a bridge architect. We worked with a landscape architect to define, again, the design language. What are the factors that go into distinguishing between different kinds of sound barrier designs? This is a landscape design problem, essentially. So this is the design vocabulary that we started with. Obviously, what the wall is made of, the texture itself, matters, because as we mentioned before, it could be metal, it could be, there are some that are made of clear plexiglass. So very smooth, very transparent, to metal, to stone, to brick, to textured concrete. In this case, it's, you'll notice it's actually an earthen berm, which works just as well. So there's a range of these to be defined, right? So that's what we term texture. Also, you'll notice there's a lot of plants here, which almost disguise the fact that there's a sound barrier back there. So we developed another visual language term for plant complexity. And you'll notice, if you're a student of this sort of thing, that we're looking at desert or arid type plants. So this is a design language for arid lands. So the plant complexity meaning is going to be conditioned by the kinds of plants that are typically used in that domain, not the names of the plants. You wouldn't see oak trees here, and this is in Arizona, so you wouldn't see like oak trees planted in front of this, or many of the other Kentucky native plants. It would be inappropriate and they wouldn't survive anyway. But you could still use the concept of plant complexity to apply both in Arizona and in Kentucky, with different meanings attached to that are specific to the landscape architects that work in that particular bioregion. So, plant complexity. Also, topographic variation. Now, what we mean by this is there's the barrier itself, and then there's the approach to the barrier, because it's not necessarily the case that we just have flat ground that comes right up to the edge of the barrier. This is especially true when you have an earthen berm that can be shaped in many ways itself and blended into the landscape, but it's also true for other kinds of more vertical barriers. So the topographic variation that approaches the barrier. You'll notice we talked about plant complexity. We didn't talk about the size or the extent to which the plants obscure the barrier itself. So obscuration can be a factor, the extent to which, or the percentage of the actual face of the barrier that are obscured by plants. Value is simply, if you remember, we talked a bit about bridge color value. Value itself, in this case, is pretty simple. If you're a painter, you know this means light, medium, and dark. It doesn't mean red, green, or blue, because those colors, that could matter, but we're trying to take a simpler path to this and just say we're going to look at whether the basic coloration of this is light, medium, or dark. And finally, it's also the case that the top of the barriers are not necessarily flat, right? Because the landscape, for one thing, changes, and it's not necessarily required that the top of the barrier, even if it's a vertical wall, be flat. A source of variety and aesthetic input can be varying the height of the top of the barrier. So we introduced a term called undulation, and again, we assigned visually with the landscape architect the meaning of that. And you can easily imagine where a perfectly flat wall is obviously low undulation, and you can define visually how much undulation is moderate and how much is high or higher. And again, that design language can be agreed on by the planners, by the designers, about what those factors mean. So now we have You can see with all of this, we have a fairly complex design language that talks about, and we've sort of simplified it here. In material texture, we simplified it down to earth berm, smooth stone, and pattern stone. As I said, color values just light, medium, dark. Plant complexity, since we're working with a landscape architect who cares about this, they defined 4 flavors of plant complexity, which is fine with us. We don't care. The amount of obscuration, they decided that the appropriate amount was going to be something low would be something below 10%, moderate would be from 10% to about 25%, and anything above that would be comparatively high in this context. We introduced also something called design pattern, which is what's pressed into or displayed on the face of the wall. You see the none basic geometric curvilinear, undulation, none staggered undulation, high undulation, and topographic gradation again. So you can think about this, and then you could begin to think about, so what does this mean in terms of designs? And so from the public's point of view, we put a design like this in front of people, and they say whatever they say. Again, we don't have a dog in this fight. If this is what people prefer, then that's fine. What we care about is that this is coded as, you can kind of guess if you think back. This is a stone wall. It's flat on top, so low undulation. It's next to a road, so the approach to it is flat. There are no plants, obviously. There's a sidewalk there. So you can begin to think about the coding scheme for this. And so on the back side, so to speak, part that the public doesn't see, we have a coding scheme that applies to this sample, and they tell us to what extent they like it. They rate it on their scale of 1 to 9. We get an average score. We look to see if that score is split, and if it's split, then we talk to them about that and try to see the extent to which we can get some convergence. But anyway, you can see how this would work. And so now here's one. So now we got a little more. There's a little bit of plant variation. You can see the approach to the wall undulates a little bit. The top of the wall is not perfectly flat. So you can imagine what the codes for this wall would look like. And we ask people, what's the visual appeal of this? And then more complex plants in front of it, taller plants, more of the wall is obscured. The ground in front of it undulates. The top of the wall has some irregularity to it. There's a different code for this. And then here's an interesting one. This is actually an earth berm. It's a sound barrier. And so it's fully an earth berm. Top is flat. There's a little bit like low complexity of plant growth. Plant's not really obscuring it. But it's another different style of sound barrier. And it has its own code. And again, people tell us the extent to which they find it aesthetically suitable or not. Now, remember that all of these decisions and all of this process fits within the larger design problem that the TOD and the landscape architect have. They would quickly point out that, yeah, an earth berm, look at the footprint of that, how much space it takes. And that's exactly right. In some cases, the design envelope, in particular instances, won't allow an earth berm because of the footprint of it. In other cases, it is. So sampling it doesn't necessarily mean that we will always do this or we will never do this, but knowing the extent to which particular kinds of earth berm designs are preferred in places where that's an opportunity, then the designers will have some guidance on how to use earth berms if they choose to do that. And there are circumstances where they'll have excess dirt from excavation from building a roadway, and so an earth berm is an appropriate way to build a sound barrier. In other cases, it's not. So all of those other factors are not trumped by people's preferences for different kinds of designs. This is additional information that helps inform what they're doing when they're making decisions. So just to give you a little notion of what that looks like, the field of fuzzy set analysis primarily lives in mathematics, but there are folks who work now in the application of fuzzy set to these kinds of complex problems. This is a screenshot, basically, of the model of people's preferences from a particular community where we showed them those samples that you just saw and more, so that we had our sufficient sample size. And if you think about it for a minute, we have, well, you see here on the map, we modeled 5 of the 7 factors. So we modeled, see number 1 there, you see HT is height, number 2 is color, so that's color value, remember. 3 is texture, so that's what the wall is made out of, whether it's earth or stone. 4 is a plant coverage that we talked about, and 5 is undulation. So if you think about that for a minute, you can't see in 5 dimensions. So in order to look at anything visually so that we can show this to you, we had to freeze 3 of the dimensions and then show you how the other 2 relate to each other. So we've frozen texture, and this, so you see texture, this number, because of the way we coded it, means that we're looking at a stone wall. Coverage, because of the way we've coded it, means we're looking at the 11 to 25% coverage, so moderate coverage from the plans. Undulation, 109, in the model that means that's low undulation. In other words, it's flat on top. So we have a stone wall with slight coverage, with moderate coverage from the plans, and a flat top. So what we're interested in is, under those conditions, what do people's preferences look like when we look at height from low to high, and from color from light to dark. So if you look at this for a moment, you see, so the purple areas, this vertical surface is people's preferences that we measured and modeled. So it's based partly on the samples that we drew, and then the rest of it is a modeling of their anticipated preferences. So embedded in here are observations, but also modeling that is a result of the combinations of those operations, of those samples. So just take a look here for a second. So if we think about it right here, so we're at a short wall that's light colored, and that's about medium. The light blue is kind of in the middle, so that's moderate preference. So if you follow this, you notice it starts to go down. So this starts to indicate decreasing preference. So anything from blue into the orange range indicates preferences that are below average, and orange indicates here very low preference. So for example, we're looking at this is a tall wall. Our color ramp here goes from light to dark. So a tall, dark wall is very much unpreferred. Now that may seem intuitive to you, but it's not necessarily the case. That may depend on the type of wall. With this type of wall, it was not preferred. But we're more interested now in the areas where there is preference. So we see here short wall with medium colored stone. There's a high ridge of preference, and that extends out up to wall height that's moderate height. And at moderate height, that preference continues to be high even if it's dark. But as soon as that wall starts to get higher, then preference starts to drop off dramatically. So the difference between a medium height dark colored wall and a tall dark colored wall is dramatic. It jumps from high preference to very low preference. Now there's no way that folks in a public meeting could tell you these things, because they don't really know them themselves. They don't think about them in that way, but when they are presented with these visual samples, they know what they like and they know what they don't like. And so this is a way of allowing the public to contribute to your project in a productive way by putting a part of the design envelope in their hands and presenting it to them in a way that they can give you useful feedback. There's no other way that you could pursue wall design and get this kind of information. We have observed on major bridge projects public involvement folks sitting down with maybe 30 people in a room and a flip chart, and these are bridges that are going to cost several $100 million, and saying, okay, what should the bridge look like? Well, that's not fair to anyone, because no one sits around and talks about bridge design. Folks that's not the kind of thing that they can say. I mean, they'll offer some ideas. It's like, well, it should be, it should look transparent, it should look nice, shouldn't be too busy. But how are they supposed to respond to that? And if one person throws up an idea and it's written on a flip chart, what does that mean? You have one comment from one person that's sort of vague, and you don't really know if other people agree with this, or even if they would know how to agree with it, because they're not really sure what this other person might mean when they say it should look nice. So all of that kind of exploration of complex design problems is really a waste of time and an insult to the people in the room. So we don't argue that you do this. You at least start, even if you're not going to use any sophisticated analysis, at least put things in front of people that allow them to respond accurately and creatively and honestly to the real thing that you want to know. Do enough work to make it possible for them to give you useful feedback to help with clarity. Okay, end of that rant. So, as we noted, there's high preference, there's low preference. We've talked about this. So design recommendations. So this is basically what we wrote into the message to the designers. This is part of our report. So we said, verbally, we show them the slides, but verbally we say, medium value smooth stone combination with undulating topographic variation and a high degree of plant complexity. And what that means is about 25% total coverage, and this is from a distance of 40 to 60 feet. And then we gave them a picture of a wall of this type, which basically is the one that we just showed you when we introduced this. Again, it may not be possible to put an earth berm in every location. It may not be practical, there may not be the earth, there may not be the space, but we can provide, this is like the most preferred design, and as you saw, there's a whole family of design combinations that are specific to every kind of wall material. So the one that we looked at was a stone, the highest preferences for stone walls, and similarly we can return preference ratings for different kinds of combinations if the design team comes back to us, or we can simply, as we did here, provide them with a more or less full report that they can just go back to. So it's a document that is basically a community knowledge base that now informs their process forever in that project. And we don't have to keep going back to the public and say, well, what about this? Because we've already asked them and we've already captured that and we already know what it is. And this kind of process, which seems like it's complicated on the backside, but it's not complicated for the people doing it. We make their process very simple. They simply have to sit down and tell us what they like. And we spend some time looking at all the different samples and talking about them until they feel comfortable. And then we say, okay, are you ready to tell us, how you prefer these different designs compared to each other? And when they say yes, then we do this. And you can see that the satisfaction with the process, not surprisingly, is typically higher than overall average satisfaction with any one design, because as we've discussed at length, you're not going to please everybody no matter what you decide to do. And so, in a way, you should always expect the process satisfaction to be higher than the actual satisfaction with whatever the chosen design is, if you're doing your process right. So now it's easy to start thinking about this. Let's think about, I mentioned land use planning earlier, let's think about that. So how would we talk about land use planning? We have a map here, a community viz shot of 100 acres of nowhere in particular, but a generic development question. And so we pose to the folks, basically, what do you want new development to look like? Because that's always the problem. The stuff that's already built is built. What do you want to be when you grow up and when you grow out? Well, how do we think about that? Well, who do we talk to? We talk to the planners, because they're the folks that have to know, they have to get information from people's preferences that makes sense to them. But how do we get people to tell them what their judgments are? What are the distinguishing properties of the developments? And these are the kinds of things, with some debate, I won't say debate, we spent some time talking about what were the most important distinguishing features of a design, of a land use planning problem. And so they said, well, housing mix, in other words, how much single family versus multifamily versus apartments, what's that mix look like? Land use mix between residential and commercial, the walkability of it, how easy is it to walk around? How ped and bike friendly is it? What's the connectivity of the street network look like? Because that has important impacts on how easy it is for people to get in and out of their neighborhoods, and for emergency vehicles to access, and to make basically people's travel more efficient. And then how much green space? So you see we have 5 factors here. So again, we sat with the planners and we said, okay, we're talking about a specific part of the land use spectrum, which is basically small town and suburban development, which is where most of the development happens. Now it's suburban development around big cities, or small towns that are growing, or they're growing out, or they've had some impetus from a development that suddenly they need to put in a bunch of new housing. A place like Georgetown, Kentucky, for example, has a growing auto assembly plant, and so there's a big housing demand. And so this smallish town is now busily building new housing because there's a big demand for it. Well, what do they want to be how do they want their town to look or to change as they're building, authorizing new houses to be built? What do they want that to look like? And you can imagine if you just go to a land use planning meeting that there's often a lot of this toing and froing about, builders are like to claim that, well, we build these kinds of neighborhoods and people buy the houses, so that must be what they like. And of course, in the absence of any other kind of neighborhood to choose from, that's not really a sample. I'm not saying that they're wrong, I'm just saying that's not an argument that that's the best way to do this, that it's the most efficient. It's the only way made available to folks. So, sitting down with the planner, how do we talk about this? Let's talk about a mix of housing types. In that kind of environment, in a suburban environment, what would be typical low-end and high-end mixtures of single-family detached versus multifamily housing? And so the parameters that we came up with said that anything from 80 to 100% single-family detached would be, a low mix. Obviously, it's all single-family detached. Medium would be if you have about 1 in 4 that are some kind of multifamily unit. High would be if half of them are some kind of duplex, apartment, something like that. Again, in a suburban setting. Mix of land uses, low would be, you could figure out how this works now, 10% of the space is given over to commercial. Medium would be about 1 in 5 acres. High would be something around 1 in 3. You're not looking, this isn't New York City, so you're not going to have packed in commercial property. Anything above about 30% of the space given over to commercial is probably going to feel like a pretty high ratio in a suburban setting. Proportion of green space, something below 5% is probably pretty low. Moderate would be around 1 acre in 10, and high would be 10 to 1 acre in 10 to 1 acre in about out of every 7. That would be a 15%. So again, a ratio that seems about right for a suburban area. How do you talk about walkability? Well, there's tons of literature out there on walkability, and we had to invent a measure or a proxy that we thought would capture that, an approximation of that. Remember, we talked at the beginning about these being categorical variables, that this isn't about precision, this is about the general relationship of a factor, which one's lower, which one's higher, which one's in the middle. And so we used, because we're building these samples in GIS with CommunityViz, we could measure the sidewalk surface compared to all the hard surface, compared to the roadway surface for cars. And so that ratio, if it's below 10%, we considered it low. If it's at 20%, it's medium. And if it's at 30% or higher, then that's a high ratio of sidewalk surface to road surface. And then the connectedness actually is a little math problem. You don't have an intersection unless there's at least one street coming in from the side. And when it does, then you have 3. Right, a minimum of 3. And the maximum, unless you're going to have complicated 5-way intersections, the maximum number of spokes is 4. So your total range of the definition of connectedness is between 3 and 4. And so we simply took a ratio in every sample of the average number of spokes at an intersection, and then we said anything, from 3 to 3.1 is obviously very low. It means there's almost no cross streets. Up to a maximum of around 3 to 3.6. You're never going to have a perfect grid everywhere, nor is that necessarily desirable. So that's our high range. So again, we assigned values to this working with the planner. So what does that mean? Well, as you might figure out, that means there's many, many, many kinds of development patterns. And so what we did was we carefully assembled 12 samples, and you don't have to memorize this, but you can see how we spaced out the samples on our coding sheet so that they would represent different mixtures of housing types, land use types, green space, walkability, and street connectivity. This is where fuzzy set analysis becomes really useful, because all the empty spaces are ones that could potentially be samples, but that we're not going to sample because there's simply no time for people to do that. So 12 samples. So here's an example of what that looks like. Here's the visual sample for scenario 1. Scenario 1 is your typical loops and lollipops. You'll see there's no green space, all single family housing. Lots of dead ends and loops. This is a very common development pattern for developers because it's, from their point of view, it's very efficient. They use every last speck of land to build a house on that they can then sell, including have a minimum street network because, of course, the street network takes up space that they could otherwise build a house on. So this is a very typical kind of scenario for a planner who's trying to maximize their land use. And so part of the information we provide to the public is what we basically tell them what's kind of obvious here. It's all single family, it's all residential, there's no open space, there's very low ratio of sidewalks to drivability. The network connectivity is almost right at 3, and it'll hold 750 people, just to give them a point of reference. Contrast that with another scenario. This is scenario 10. So now this takes a little bit more time. You can see the residential area with a single family. You can see in this particular case, we distinguish between townhouses and multifamily for purposes of the public being able to understand it. Those two were combined to give us ratios that we coded. But in this case, you will see there were townhouses, but not multifamily. So basically twin homes, but no apartment buildings here. You see where the commercial district is, and you see how much of it there is. You see that where the parks are. So in terms of coding, this has a completely different coding scheme than the other sample. But from the point of view of the public, and you can see the performance of it, from the point of view of the public, it looks like this or something like this. So they get a better feel for what we're talking about. You can see residential, single-family residential around the edge. You can see the townhomes. You can see a commercial district. You can see a park in the background. It gives them a much better feel for what we're talking about when we say this and when we show them a map like this. Because I'm a geographer, maps mean a lot to me. Many people cannot read maps, and to show them this and expect them to understand what you're talking about is not fair, and not only is it not fair, it means you put the accuracy of the information you're gathering from them in peril, because if they don't understand what you're showing them, then you can't trust the replies they give to you, right? So you sacrifice clarity if you don't provide clarity. So we do this. You notice there's scenario 10. I said we had 12. And so we get interesting things like this. We've now sort of reviewed what this looks like. So in this case, we're looking at housing density on this scale. So here's single family detached all the way up to that maximum we defined as 30% multifamily. So single family detached, maximum about 30%. BLU is land use. So here is all residential. Here is the highest level of land use that we talked about. So you see how that scale goes. Everything else is fixed. So green space, as I'm pointing out up here, the code means there's very little park space here. The sidewalk ratio is quite high, so there's quite a bit of walkability. Street connectivity is moderate, so it's somewhere in between the two samples that we looked at. Under those conditions, you can look and see what folks' preference look like for different combinations of housing density and land use. So we're looking at what are the combinations of housing density and commercial to housing space that people prefer. And you'll notice here where it's all single-family detached and there are no commercial buildings, preference is quite low. Then you'll also notice that when you take the housing density all the way up and you take the commercial density all the way up, at 9, preference is also low. So there's two different dynamics going on in terms of people's preferences. And you can see in between, remember blue is moderate or just slightly better than moderate. So this is sort of acceptable, but it would hardly be characterized as preferred. So let's see what happens if we change one factor. Let's jack the green space up. Remember, it was low. Let's take green space up, and let's take street connectivity up. Everything else is the same. And look what happens. Now, the idea of having higher density housing and higher density commercial buildings is actually strongly preferred. Because these other factors, the fact that we now have enough park space and we now have enough street connectivity to make these work, has made this condition acceptable. Again, these are not the kinds of, this is useful now for a planner to understand this, that the ratio of the different kinds of factors that go into the planning code matter in terms of helping people tell you what they would like to be when they grow up. There's no way people could verbally express this. They can't, they don't even probably know in so many words what it is that they like, but if you show them different kinds of samples and they can respond to them, you can have reasonable clarity, in this case considerable clarity, about the kinds of combinations of factors you need to write into your comprehensive plan to have acceptable and even preferred kinds of land use plans. Let's take another one here. Here's a small area design. So now we're working with architects. This was a light rail station that was planned for Louisville when they're looking at light rail. So it's a 3 or 4 acres. We have a light rail that's planned to go through there. We have a surrounding neighborhood, and we need to talk about what kind of design they would prefer. So by now, I don't have to go through all this with you. This is the architect's language for talking about small area design: the height of the buildings, the typology of the open space, the density of the buildings, and the kinds of, the typology of the buildings, the density of the buildings, and then the type of open space. And you can see them there, and they arrange them. So we use that as our coding scheme. And for our samples, we simply use photographs of other already built places that represented different combinations of those properties. We gathered people's preferences. In this case, you can see we talked with them about it. The architect explained some of the things that were going on, and we were curious to see if people, as they became more informed about that, if their opinions would change. And you could see in this case, they were sort of moderately, they found this moderately appealing until they had more clarity about it, and then they were like, oh yeah, this is the design we like. In some cases, it was moderately appealing, and that didn't really change. It was preferred slightly more, and so on for all of them. So you can see first scoring, second scoring. What you'll notice is how the first scoring, the scores are closer to 5, and the second scoring, the scores are more distinct. The lows are lower and the highs are higher. This is what we want, because we want clarity, right? We want people to feel, to provide us information that gives us clear distinctions. We don't really care if they dislike some of them. In fact, we need that kind of information to give us clarity. So it's not a guessing game of, ooh, I think they'll like this, so we're going to put it up there. It's a visual sampling, in this case, a combination of visual and other considerations, to give us clarity on the kinds of things they like and the kinds of things they don't like, which gives the designers clearer guidance. So I'm not going to belabor you with another one of these, but this is an example of what that surface looks like. I think what we're looking at here is height is 0 to 5 stories. So we're looking at, so we're looking here. This is moderate height. So this is there's a preference for 2-story buildings actually at high densities, at high visual densities is right here. And actually as the visual density drops off, the preference drops off. See, this might be counterintuitive, because when we talked to the architects and the planners originally about what we should build there, and they say, oh, well, people are just going to want little single-family detached houses. This is not anything like that. So measuring them and giving them a chance to tell us what's going on instead of us dictating to them is always useful to the planner. So in summary, I hope that these examples have helped you think a little more carefully about when you have a complex problem to deal with. It can help you address a very highly complex questions more accurately. It provides much more clarity for professionals. It allows you to discriminate more clearly between the combinations of the different factors, because as we've noted at the very beginning, the way these factors combine is not linear. It's factually can be in any direction. We really can't anticipate those. For the methodology, from the point of view of the participants, is not any different than comparing anything else. They don't really see what's going on in the background, nor should they have to worry about that. We simply put in front of them what they need to see to give us what we need to know. And that data, once it is captured and modeled, becomes a permanent part of the project. So if later conditions change and some other factors, the cost of building something or the footprint changes or whatever, the price of steel changes, you can go back into the preference model and requery it. You don't have to come back to the public and say, well, what about this? It does require more time and money. It requires more care and thought. And so folks are reluctant to do that, and that is perfectly okay in projects that are not very big or well funded. You can use the scenario approach without the fuzzy set analysis. If you're careful and you adhere to some of the other rules that we talked about, you will still get pretty clear information from folks. The point here is not to be guessing what you think they're going to like, but to be sampling across the entire range so that they'll give you clear differences between things that are highly preferred and things that are not highly preferred. Thank you for your time.